Alright, in this video we are going to work another rotation problem. It says the disk is initially rotating at 20 rads per second. It accelerates to a rate of 4 rads per second. Accelerates at a rate of 4 rads per second squared. That's got to be a typo. For 3 seconds. So let's see. I'm going to be asked to write a velocity time graph. So we have omega here, and it starts at 20. This is in rad per sec. And it says it has a rate of 4 rads per second squared of acceleration. So that's a slope of 3, or sorry, slope of 4. And it does that out here for 3 seconds. And I know if the slope is 4 and it does it for 3 seconds, it's actually going to go up here to 32. And then it says it rotates at constant angular velocity for 4 seconds. So it's going to go out like this. So out to 7 seconds. And then it decelerates at a rate of 3 rads per second until it comes to rest. It goes out like this. So that slope is minus 3. Again, need a square there. 3 rad per second square, just as this one was 4. And it says draw a qualitative angular velocity time graph. And I did that. And I would do that just because I want to get a handle on this problem. So looking at how this thing compares to the old linear stuff, this used to be the initial speed, v. Accelerates at this rate implies a slope, which is how I found the slope. The disk rotates at a constant angular velocity. That's like saying it has a constant velocity, so it's no acceleration, so it's got to have a horizontal line. Now remember, by that in linear land, we were talking about tangential accelerations. In these things, all of them have acceleration because they're all going in circular paths. Every point on the wheel will have centripetal acceleration. What we're talking about is where it has angular acceleration. And it will decelerate at a rate of 3 rads per second. That means it's got a slope going negative. And that slope is 3 rads per second squared till it comes to rest, which means it ends up down here. And that's how I figure those things out. Now, what else do I want to know? How fast is the disk going at 4 seconds? Well, at 4 seconds, it's going 32 rads per second. I got that from the graph. Now, it isn't true that you could apply kinematic equations or anything else to find the speed at this point. But we could have applied kinematic equations in here, rotational kinematic equations, because it had a constant acceleration. And that's one way I could have found this 32. I could have said, well, omega at t equal 3, omega is equal to omega naught plus alpha t, which was 20 rad per sec plus 4 rad per sec squared times 3 seconds. So omega is 32 rad per sec. That's basically what I did anyway. I just started here and said, hey, the slope is 4. I go over 3. If the slope is 4, I have to go up 12. So the rotational kinematic equations are just the same thing as I talked before about getting the information from a graph. It stays at that speed all the way out to 7 seconds. Then I ask another question. The question is, when will the disk come to rest? Okay, so I got to go back up here and think about this. I know this slope. I know how far it has to go down. It has to go down 32 units, and it's doing it at 3, so it's going to take a little bit more than 10 seconds. So I can either do it by just looking at the slope, or I get the same thing from the rotational kinematic equations. I'll use them. Omega is equal to omega naught plus alpha t. This thing here is 0. So alpha t is minus omega naught. T is equal to minus omega naught over alpha. Note that this is from 7 seconds to a later time. So whatever value we get out of this is only the time from 7 seconds. Whatever later answer we get out of there, we're going to have to add 7 seconds. Chemical equations weren't true from the beginning. They were only true during the period of time from here over, where the slope was constant. If you included from here to here, the slope was not constant. So if you want to find this time right here, you're going to have to add that 7 seconds to whatever time we find is added right there. Okay, so if this is 4 seconds, then the total time would be 11, is when it would actually have come to rest. We've got everything we need here. Minus 32 rad per sec divided by minus 3 rad per sec squared. And that's going to be 10.67 seconds. Therefore, t rest is 7 seconds plus t is at approximately 17.7 seconds is when it comes to rest. So that's when, go up here and we'd mark that right here, 17.7 seconds on our time graph. Alright, what else can they ask us? Through what angle will the disk rotate before coming to rest? Looking for displacement. Delta theta is area under an angular velocity time graph. So what they're asking me to do is to come back up here and break this up. I need to break that up. So there's A1, A2, A3, and A4. And get those areas. So 32 minus 20, this is going to be 12 times 3 divided by 2. I can put that down there. So A1 is 1/2 12 rad per sec times 3 seconds. And that's 12 over 2 is 6. 6 times 3 is 18 radians. Seconds cancel. A2 was 20 rads per sec times 3 seconds. And that was 60 radians. A3, it's traveling at 32 rads per sec, and it does that for 4 seconds. So that'd be 128. And A4 would be 1/2 times 32 rad per sec times that time. We just found the time a minute ago. It was 10.7 roughly seconds. That one I can't do as easily in my head, so I'll use my calculator. I get 171 roughly radians. So delta theta is the sum of that. 18 plus 60 plus 128 plus 171. 377 radians. Assuming I've done my calculations correctly. You can also BS the number of revolutions. I could divide that by 2 pi if they wanted to know that. Anyway, if they ask me how far did a point on the disk travel, to know the particular point's distance it traveled, you have to tell me the radius from the axis of rotation to the point on the disk you want. Is it the rim? Is it halfway the rim? Which point? Anyway, that's how you work this particular type of problem. It's exactly the same as the type of problems we worked earlier on graphs back in Chapter 2. It's on previous exams that we did problems asking you to find areas on a curve. So make sure you can work those linear problems and see how they work into angular problems for the next exams.